Assalamu alaikum warahmatullahi wabarakatuh. So today we have lecture 10. So in this lecture uh, we will study about the counting methods. Don't confuse it with the grade 1 or 2 counting methods. This is a counting method for the probability and the counting for the number of possible outcomes in a sample space, because understanding the sample space is key step in formulating and solving a probability problem. As you have seen so far that in every question that we have solved to find the probability of certain event, we first note down the sample space. But so far the sample space was very small, so we can write down the each and every outcome of the experiment. But sometimes this number means the number of outcomes could be enormous. So in that scenario we cannot write down the exact number of, so we cannot write each and every possible outcome, so we must at least know what is the total possible number of the outcomes in a sample space. So let's solve this example 2.5. It's simple. It says that choose 7 cards at random from a deck of 52 different cards. Now it says that display the cards in the order in which you choose them. So remember, here we need to put them in order. So in which order they will come, we have to put them. And it says that how many different sequences of cards are possible. So this example says that we have a deck of 52 cards and we have to choose one card and put it place it somewhere in front of you, and then choose the next card. And remember that when we will choose the next card, we will not have the 52 cards because one card is already taken, so we will have the 51 cards. So from the 51 cards we will choose the one card, and so on, unless we are filled with the 7 cards. So in this way, how many possibilities, total outcomes we could have, means for the first card we have the 52 choices. Out of 52 any of the card can come. For the second card we have the choice of 51 cards. For the third card we have the choice of 50, and so on, 49, 48, 47, and 46. So the first card gave me 52 choices, the second card gave me 51 choices, 50 choices, 49 choices, and so on up to 46 choices. So if we just multiply these small numbers, so it will be a huge number. So this number is around 674 billion possible outcomes. So we cannot list every one of them on the page. So sometimes these experiments are more complicated in practical, but there are some techniques to find the size of the sample space to that and all follow the fundamental principle of counting, and that principle fundamental principle of counting, we can write it as theorem 2.1, and this states that an experiment consists of two sub experiments if one sub experiment has k outcomes and the other sub experiments has n outcomes, then the experiment has n k outcomes. To understand this theorem, let's see this example, which is example 2.6, and it says that there are two sub experiments. The first sub experiment is flip a coin. So when we will flip a coin, so we can get either head or tail. So the second sub experiment sub experiment is roll a six-sided fair die. So obviously when we have the six-sided fair die, so its possible outcomes will be 1 dot, 2 dot, 3 dot on the top face, 4 dots on the top face, 5 dots or 6 dots on the top face. Now if we just see that this is say k outcomes and this is n outcomes of experiments, so total number of experiments in the total number of outcomes in the this sub experiment will be nk, which is 2 into 6 or 6 into 2, so it is 12 possible outcomes. So because this is a simple experiment, we can write them easily as head 1, head 2, head 3, head 4, head 5, head 6, tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. So these will be the 12 possible outcomes for these two sub experiments. So next we have this K permutations. K permutations means that an ordered sequence of k distinguishable objects. So if we have the k distinguishable objects, so we can call them as k permutation represented by n sub k. So n sub k is simply is equal to n factorial by n minus k factorial. So this is called the k permutations. So the example that we have done, this one, choosing 7 cards from the 52 cards and putting them in order, is the same as here. So that will be the 52 choose 7, so 52 factorial divided by 52 minus 7 factorial. So that will be 52 into 51 into 50 into 49 into 48, 47 into 46 into 45 factorial divided by 45 factorial. So we can see that this is the same number that we have achieved earlier. Now there is one more step in it, that is sampling without replacement. Sampling without replacement means that whenever we take an object from whenever we take an object, we will not replace it, we will not put it back in that bag or whatever. We say, just like in these 52 cards, if we take one card, so for the next sub experiment we will have 51 cards and so on. That's how we can see here. So sampling, this is called sampling without replacement, and sampling itself is known as choosing objects. Sampling itself is the choosing objects randomly from a collection is actually, or is called, sampling. And chosen object is known as sample. So we have the sample, means whenever we take something. So sampling k permutation, as we have seen, is the sampling without replacement. So k permutation, so far we have seen permutation is sampling without replacement. So there is another important thing in it, and obviously they are ordered. I'll write it here. Ordered means that in this order we will choose the object, we will not change its order. So sometimes order is not important. So if the order is not important, so means if we get different objects, so if we put them in some, means if we choose the 57 cards out of 52 cards, so as we know that they are in from 2 to 10, and then it's a J, Q, K and A. So if we put them in this in the sequential order of the cards, that whenever we get 2 or 5 and 7 and J, Q or whatever, so we will put them in order. So in that way, the sampling, the order, this order means that we are getting objects from through sampling, and during the sampling we will keep the order. Means if we get the first object, we will put it in the first place and second place and third place, so on. But if we do not bother about this order, that and we put them in our own orders, so that would be so in certain applications order is not important. In certain applications order is not important. So to understand this, let's see very basic example just to understand this concept. It is 2.7. So it says that suppose we have 4 objects. We have 4 objects named as A, B, C, D. So we define an experiment in which we choose 2 objects out of these 4, and they are without replacement. So it means that whenever we will choose one, so object that will not be chosen again. So in this way, and order is not required, so we will just put them in alphabetical order. Alphabetical order. So it means that if we choose A and B, or we choose B and then A, so they are same, because when we will put them in order, in alphabetical order, AB and AB will be the same. In this way we could have how many possibilities? We can have AB, we can have AC, we can have AD. So we cannot choose BA again, and this is without replacement. So AA and BB and CC and DD will not be possible here. So it will be BC, BD, and then it will be CD. So we have also arranged them in alphabetical orders. So we can count it here: 1, 2, 3, 4, 5, 6. So we have the 6 possible outcomes. And it similarly says in the next example that if we put them in order, means example 2.8. So it says that if we put them in order, so what will happen? So in that case, AB will not be equal to BA. So these two will be different if we put them in order, not in alphabetical order. Order means order of sampling. So if A comes before B, so that will be this one's outcome, and if B comes before A, that will be another outcome. So in that scenario, our sample space will contain possible outcomes would be AB, AC, AD, again BA, BC, BD, because they are without replacement. So BB and AA, CC and DD will not be possible. Similarly CA, CB, CD, DA, DB, DC. So in this case we see that these are 12 possible outcomes, and these 12 possible outcomes are the K permutations, and K permutations by formula also we can find out here, n choose k, which is n factorial divided by n minus k whole factorial. So here n is 4, choose 2, 4 choose 2, so it will be 4 factorial divided by n minus k is 2 factorial, because 4 minus 2 is 2 factorial, so it will be 4 into 3 into 2 factorial divided by 2 factorial, so which is 12. So what about the previous example in which order is not required? To find that, we have we call them as the k combinations. We call them as the k combinations. K combi. So k combinations, we have seen that in example, previous example 2.7 and 2.8. So in 2.7 we have the 6 outcomes, and each outcome in example 2.7 is a subset of the outcomes of k permutations in example 2.8. So to denote this combinations, so we define this as a theorem. It states theorem 2.3. So the number of ways to choose k distinguishable objects out of n distinguishable objects is n choose k, which is n factorial divided by k factorial n minus k factorial, which is actually equal to k permutations divided by the k factorials. So the order will be reduced by k factorial. Obviously combinations will be less than the permutations. So we can choose we can write it as a definition, n choose k here like this, for n factorial divided by k factorial n minus k factorial 0 for k is equal to 0, 1, 2 up to n, and this is otherwise. Now why we have written this definition in this form? Because k cannot be any floating point number, or k cannot be greater than the n, and k cannot be negative. So k cannot be floating number like 2.8, 2.7, or it cannot be more than n, just like in the previous example. So n choose k cannot be 4 choose 5, and because we cannot find the we cannot find the negative factorial for right now, for at least for this subject. So this will be the 3 limitations for this basic definition. So that let's see this one simple more example. It says that it's example 2.10, and it says that there are 4 queens in a deck. As we know, there are 4 queens in a deck of 52 cards. So you are given 7 cards at random from the deck. What is the probability that you have no queens? That you have no queens. So this is a very interesting example. So first of all, again we need to find out the sample space. So we have to choose 7 cards. So sample space would be, say we call it as H. So that will be 52. Choose 7 cards. So that will be our possible outcomes, and because each possible combination of 7 cards, each with probability, each card has the probability of, each with probability of 1 over H. So each possible outcome could be 1 over H. So next we want to see that if we have we have 7 cards, so if we get no queen, so we call it as H and Q. So if it is no queens, means we assume that it is 42 minus 4, choose 7, or which is 48, choose 7. So the probability will be probability of receiving no queens is the ratio of the number of outcomes with no queens to the number of outcomes in sample space. So it means that it would be H no queen divided by H. So this probability will be approximately 0.5504. So there is another interesting method to look at this problem. So that would be making a tree. So how we can make the tree? So if we start with this, so we have 4 queens actually. So if we get, say, on the first hand we get the card with which is the queen, so that's the probability of getting first queen is 4 over 52. And if there is no queen, so what's the probability? That will be the probability 48 by 52, because we were considering no queen here. So if there is no queen, so we can move on to check another card. So if we get Q at the second attempt, so obviously for the second attempt it would be 4 by 51, because we are dealing with the sampling without replacement, and similarly this one will be 47 by 51, because we have chosen one card which is not queen. So this is N2. Similarly, if there is no queen, we will move further and say that we get, say, Q3, and its probability is 4 over, again it will be reduced 50, and for the no queen it would be 46 by 50, and so on. We will move until we reach here. n7 because we are selecting n cards, so it will be 4 over 46, and again this will be 42 by 46. So the probability of having no queen in the 7 cards will be just simply the product of all these probabilities. So it will be 48 by 52 into 47 by 51 into so on 42 by 46. So that will be again approximately 0.5504. So I hope you have understood this sampling without replacement, the combination and the permutation, how we can use them to calculate the sample space. So we will continue with the next subtopic of this sampling with replacement in the next lecture inshallah. So stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuh.